Okay, so today we are going to start studying systems of linear equations. The type of equations we will consider are like this. Here we have a matrix Aij. It's an n by n matrix. Here I have n equations, right? Here n equations. And we have n unknowns. ARGs and BIs are in the field K, and these are the unknowns. Letting A be the coefficient matrix, this is called coefficient matrix. I can write this equation like this. See that this is nothing but for this system. Can be written as AX equals B is a matrix equation in matrix form. Okay. Of course, writing like this, it has many advantages. First remark, a system like this, there are three possibilities. A system executed B may have a unique solution with no solution or infinite many solutions. Okay. Let me give some quick examples where all these possibilities are, all these possibilities occur. For example, let's consider this equation, this system. Let's say x plus y equals 5, 2x minus y equals 7. Okay. So this in matrix form is what? This is 1, 1, 2, 1, right? 2 minus 1. And then here I have xy. Let me just use xy instead of x1, x2, since I have only two variables. It's easier to use x and y instead of x1, x2, and then we have 5, 7. So in matrix form, this is our equation. What is the solution of this? I may use this matrix form, but we know how to solve this from elementary school, right? How can you solve this? Well, just add them up, right? If you add these two equations, you get 3x equals 12, right? And then from this, we get x equals 4. And if x is 4, then y is, of course, 5 minus 4, which is 1. So the only solution we obtain is that hence xy equals 4, 1 is the unique solution. Of the system. Okay. Of course, we could. So this is the unique solution. I could just obtain this solution using this matrix equation also. How? Well, we have this matrix 5, 7. I could just multiply this equation by the inverse of this matrix. So 1, 1, 2 minus 1 inverse. Well, of course, one should ask does there an inverse for this matrix? Well, its determinant is -1, -2, -3. So it is not 0, therefore it is an inverse. 1, 1, 2, -1 times xy. So I multiply both this side and this side from left with the inverse matrix. So what we get? Well, here you multiply this matrix with its inverse, so you get just identity matrix. Here, okay, I have here, of course, 5 and 7. I think that 5 and 7. Now here I have to really compute the inverse. What is the inverse? Inverse is 1 over the determinant. Determinant is -1, -2, -3. And then you do what? You interchange diagonal entries, right? So -1 and 1. And multiply off diagonals by -1. So -1, -2, and 5 and 7. So this is -1 over 3 times -5 -12 -10 plus 7, which is just 3. So this is just extra there. So this is just 4 and 1. Here, of course, this is just xy, right? When we multiply with identity, you just get x, right? So you get the unique solution. So this is an example where the first possibility happens. Here I said this system may have a unique solution, and we have seen one example, unique solution. There might be the case where we have infinite many solution. So second example, look at this equation. Well, if you write in matrix form, this is just 1, 1, 2, 2. Ya da aslında neyse tamam. Okay, xy. I cannot just do what I have done over here because this matrix is not invertible. So A here is just 1, 1, 2, 2, and determinant of A is just 0. Therefore, hence A inverse does not exist. Okay, does not exist. And actually, if you solve this, what you get? So I cannot use this, matrix stuff. We have to just solve it, by hand. Well, you see that this equation is just this equation multiplied by 2. So this doesn't carry any information actually. I can just cross that out, right? They both say the same thing. So this is the only equation actually. What are the solutions of this? Well, for any value of x, I can find a y value so that this is satisfied. I can choose, for example, x equals 0. In that case, y will be 5. I can choose x equals 1, then it will be 4, right? This way, we see that there are infinitely many solutions. So this has this equation has infinitely many solutions. Namely, let x equals t, for example. any real number or any field element, whatever. Okay, this choose real numbers here. Then y just 5 minus x, which is 5 minus t. So, and these are all the solutions. So, the set of all solutions is what? X comma y, y's, where x is just t and y is just 5 minus t, and t is a real number. So we have infinitely many solutions. Okay?
K is finite, then B is finite.
Yeah. If the field is finite, then of course we have only finite many solutions. What about no solution case? So here maybe I should say that infinite solutions. Infinitely many solutions exist, of course, if your field is different. Okay. If it is finite, you have only finitely many numbers, so you cannot have infinitely many solutions. Right? Infinitely many solutions exist only if you have, your ground field is infinite. Okay, now third example. Let's look at this system. X plus y equals, let's say, 5, and x 2x plus 2y equals 7. Okay. Well, if you have something like this, of course, you see that this has no solution, because if x plus y is equal to 5, then 2x plus 2y equals 10. But here you said that 2x plus 2y is equal to 7, right? Well, this means what? 10 equals 7. This is a contradiction, right? A contradiction. Why did we arrive at this contradiction? Because we assume that there are x and y, so that x plus y is 5 and 2x plus 2y is equal to 7. If you assume this, if you assume that there are such real numbers x and y, then you arrive at this contradiction. So this means that such a system has no solution, cannot have a solution. Okay. Hence,
No. Depend on our code, right? If you choose our code, then that's the one that solution.
That's 7.
Yeah, I mean, it was
Well, it will not be again.
not 7.
Yeah, it depends on your field, of course. But here, let's say we are ground field R. Okay. Hence, this system has no solutions. So we should expect all possibilities: unique solution, infinitely many solution, or no solution. If your ground field is finite, then of course, instead of infinitely many solutions, you may have finitely many solutions, but larger than 1. I mean, you may have, for example, not unique solution, but 10 solutions. If your field is, let's say, finite. 10 olur mu emin değilim ama. Yani bir asal sayı işin içine girmesi lazım. Anyway, we will see two different methods. One traditional method, which is called Gaussian elimination, we will do that. And another method, which is given in the book using exterior products and so on. I will first do one case using this method, I mean the method given in the book, and we will see so-called Kramer's rule. Maybe you have seen in high school or dershane. In general, its proof is confusing and so on, but once we have this exterior products and so on, it is easy, and we will do that. Okay. First, we consider systems of the form on, let's say, AX equals B, where A is an n by n matrix, n by n invertible matrix. Of course, if it is, if A is an n by n invertible matrix, it has an inverse, right? So N has an inverse. And thus we have the following. I can just multiply the equation by A inverse, since it exists, and here we get A inverse and then X equals A inverse B, and here this is just identity times X equals A inverse of B. Therefore, X is just A inverse B. So this is the solution. So what is the conclusion then? If we have a square system, meaning that if the coefficient matrix is a square matrix, what does it mean? You have n equations and n unknowns. And if the matrix has non-zero determinants, in other words, if it is invertible, then the system has a unique solution. So we can write this as a corollary. If the coefficient matrix A is a square invertible matrix, then the system has this system, which system X equals D, has the unique solution, which is A inverse of A inverse times. Okay, and this is the proof. And you just multiply both sides by the inverse of the matrix A. Okay. Now, what is the Kramer's rule? Let me tell you what it is. Of course, finding A inverse in general is not an easy task, right? In finding the inverse matrix. You will see some methods to find the inverse, but in general, it's a complicated business because you have to compute lots of determinants and so on. There is no easy way, but you can do that without computing determinants. I will show you later how we do it. But there is a nice method called Cramer's rule, which tells us how we can find the solution in this case. So we have this system. Is an n by n system, okay, n by n system. We have n unknowns and n equations, okay. All right, so now if okay. You see, if the column, let's say A1, A2, AN, these are the columns of A, okay? Columns of A. So what is A1? A1 is the first column. A1, 1, A2, 1, AN 1. What is A2? It is the second column. A 1, 2, A2, 2, A and 2. Okay, and so on. First column, second column, and so on. Now, in that case, you see, my matrix equation will be like this. So if I have these columns, A and, okay, so these are the columns, and here I have x1, xn, which is equal to v1, vn. Then we have what? Here, I assume that determinant of A is not zero. Okay, so A is inverted. So we are considering this case. Now, you see what happens here. The elements in the first column are multiplied with x1, right? Because whenever you take a row and multiply with this, the first element here is multiplied with x1. Here, the first element in the second row is multiplied with x1 and so on. So this product is nothing but actually this x1 times the column vector a1, and then x2 times a2, and xn times an, and that's equal to this this column vector, which is b. So A1 is this one, A2 is this one, AN is what? AN is just the nth column. So 1n, 2n, and okay. So I have this equation, and then we do what? Since determinant is not zero, the columns and rows of this matrix must be linearly independent. Because if they are linearly dependent, then we know that, well, actually, let me just say, what is determinant of A? Determinant of A, you can just take this digit as vectors and take their exterior product. So this is just A1 H. Actually, I should say this. If I take these columns and take their exterior products, what we get just determinant of A, and this is not zero. Okay, this means that these columns, so A1 up to AN, these are linearly independent, but we are in already Rn or whatever, n-dimensional vector space, and I have n many linearly independent vectors. Therefore, this is a basis. So, is linearly independent, and thus it's a basis.
Yine bir tarafta kalmış.
Okay. So we are doing Kramer's rule. We assume that we have a square system. A is an M by N matrix, and its determinant is non-zero. I wrote my matrix in this form. A1 is the first column, A2 is the second column, AN is the nth column. So these are the columns of A, like this. Then this matrix equation can be written like this. And if you think about this for a minute, you see that this matrix equation is equal to this equation, namely x1, let's say, is a number, scalar, multiplied the first column, x2 times the second column, xn times the nth column is equal to the column B. We are given that determinant is not zero, but we know that determinant is nothing but exterior product of columns or rows. I could have done something similar to this one and just write the determinant as the wedge product of rows. But I prefer this one. Since this product is the determinant and we assume that determinant is not zero, it means these vectors are linearly independent. But we are already in the space K n, right? Because our vectors are n-dimensional, right? These are in Kn. We are in a n-dimensional vector space, and I have n many vectors which are linearly independent. Therefore, this is a basis for Kn. So, this thing, A1, A2, An is a basis for Kn. Actually, maybe I should say these are column vectors, Kn times 1, right? Column vectors. Okay. Then we do what? Well, if I have a basis, I have a dual basis, right? So let me call this data. Consider the dual basis. Vector star, A1 star, A2 star, AN star. What are these? These are homomorphism from the vector space to scalar fields. And what they do, they need vectors. The R vector is a J vector and gives us theoretical data Ij. If they are the same, we get 1, otherwise we get 0. Okay. Well, then we do the following. What is AI star applied to X? Well, X is this, right? X is this. Bir dakika. No, not X, but evet, vektör olması lazım. Şöyle, pardon. D'ye uyguladığımız zaman diye. Ups. Özür dilerim. Let me apply to this B. We get what? B is just AI star. B is just right here. B is this digit. So it is just x1, a1, xn, an. These are scalars, they go out. So this is x1 times a I star applied to a1 up to xn ai star applied to an. Well, these are all zero except the ith one, right? Because they are dual vectors. So the ith one is 1 and the coefficient is just xi, right? So xi times ai star ai, but this is just 1. So right, this is just 1. So we have xi here. Okay. Şimdi buradan ne çıkar? Aslında bunu yapmaya gerek var mıydı? Gerek de yoktu ya. Dual elemana. Neyse yani şey evet. Dual elemana yapılıyor. Okay. Actually, I didn't need this, but nevertheless. We will do the following. Consider the product. Efendim? Yes.
Is this the solution of the first equation? X.
Xi is the ith entry here. Okay, so this is the unknown vector. Xi is the ith element. So if you know the dual elements, then you know what is xi. Dual element applied to B. Okay, but actually we can so right. This gives us the ith element of the solution vector as this number, which is the dual vector, ith dual vector is applied to B. Okay, now I'll do something actually different. Let me consider this. A1, which A2, which here we had AI, right? Let's skip AI, but write B here. So maybe I should be more careful here. I have AI minus 1. Instead of the ith vector, I write B and then I plus 1, and I go up to an. Okay. Now, what is this? This is just, so B is this vector. So this is just A1 H up to AI minus 1. And then I have B. What is B? B is that vector over there. So it is x1 times A1 and so on up to xn times an, wedge product AI plus 1 and then up to an. Okay, now on one side, this is what? This is the determinant of a matrix, which matrix, determinant of this matrix. First column is A1, A2, and then ith column is not A but B, okay? And then, so the ith column is B, okay? And what is this? Well, I can open this product using, this term. Here I will have A1 wedge product with these gadgets, but I have already A1 here. So this A1 wedge, this A1, it will give me 0. Therefore, this term has no importance. I can just delete it because when I open this with respect to this element, this term will give me 0. So this is gone. What about A2? Well, that will be gone. Only one of them will survive. Which one? Here I have AI or XI AI. Şunu şöyle yazayım da sileyim. Bir türlü oluyor. Okay, here we have XI AI, XN AI, and then I have this gadgets. So when I open this up, I will get A1, A2, AI minus 1, and then only the ith term will survive, and that is just xi times AI. All the others are gone, and then AI plus 1 and AN. And this coefficient, of course, goes in front. So we have just xi times A1, A2, AN. But what is this? This is the determinant of A. So this is just xi times determinant of A1, A2, AN. So it is just xi times determinant of A. Okay? Determinant of A times, sorry, this thing is not determinant A, it is determinant A times determinant A zaten. Tabii ki. Yani bunları vektör olarak görürsen bunların yaptığında bir sayı çıkacak, o sayı. Tamam. Determinant A. Peki ne elde etmiş olduk? Bakın. So if X, which is A inverse B, is the solution where X is this given, X1, X2, Xn, then what is this Xi? Xi is the following. So this element is what? It is this determinant divided by this determinant. So it is just determinant of A1, A2, B, AN divided by determinant of A1, A2, AN. Right? So that's the Cramer rule. You can prove this using other definition of determinant and so on, but it's not, it's more complicated. Once we used to this cancer product and so on, life is easy. Okay, let's do one example. Yani tabii Burada şey var. Aynı. Tamam mı?
Efendim? Anlamadım. 30 oldu. Okay. Alright, let's stop.